me and Mark did it once, and I couldn't believe how easy it was. So I was like,
what platform were you doing it on? Were you on a Mac or on a
PC?
A PC? Maybe I'll just come back to you. I think there's something very simple I'm missing about how to make all of this work better.
It was a while ago that I made it work, but I did make it work once.
Great.
Which means I probably could make it work again.
Okay, so we were talking about Tutte polynomials. I defined the Tutte polynomial for you in two ways. And what I want to do today is give you more reasons to care about the Tutte polynomial. We're going to see, let's just say, some of the many applications of Tutte polynomials. I could really go on about this for a long, long time. There's a whole book about it. Which, if people are interested, this is a very good book. Complexity, knots, colorings, and counting. It talks about different applications of Tutte polynomials in knot theory and statistical mechanics in different places. And I'll show you a couple of these. Okay? And let me start by recalling what I said last time, which is basically that the Tutte polynomial is the mother of all invariants that satisfy a deletion contraction recursion. So if f is a Tutte-Grothendieck, or I said even a generalized Tutte-Grothendieck invariant, which meant that the function at a matroid, well, first of all, the invariant implies that it should be constant on isomorphism classes. So two isomorphic matrices have the same invariant, which satisfies this linear relation between the invariant at the matroid and its deletion and contraction. For E not a loop or a co-loop. And then if you do have a loop or a co-loop, then you just take the function of either the loop or the co-loop and multiply it by the function of the deletion. So these are generalized Tutte-Grothendieck invariants. And we said that any function that satisfies these properties is just an evaluation of the Tutte polynomial, and there's an explicit recipe. And it says you just do this. A to the number of elements of the matroid minus the rank of the matroid. B to the rank of the matroid. And then the Tutte polynomial of the matroid evaluated at f of the co-loop divided by b and f of the loop divided by a. So if you're able to determine a, b, f of the co-loop, and f of the loop, you have the whole function. I should warn you that I made a mistake when I told you this last time, and I flipped these a and b. So this is the right way, but I got these wrong last time. Okay. So make sure to never use the incorrect version. Okay. And so basically what I want to do is just use this recipe for a bunch of things that we care about. So for example, an invariant of a matroid is the number of bases. Okay. And remember what I said last time, that if you count the number of bases of a matroid, then you can separate them into two classes, the ones that contain a specific element and the ones that don't. The ones that don't contain the element E are just the basis of the deletion, and the ones that do contain E are just the basis of the contraction with E appended to them. These are the bases not containing E, and these are the bases containing E. This goes for E not a loop or a co-loop, and it's easy to see that there's two things to check. And in the whole class today, I'm just going to check the first one and ask you to check the second one, which you can do in exactly the same way. Okay. But that means that this is Todd-Grothendieck invariant, and I can apply this recipe. Here, A is equal to 1, B is equal to 1, and all I have to do now is compute f of the coloop and f of the loop. So how much is f of the coloop? How many bases does a coloop have? Coloop has 1, right, which is the coloop itself. How many bases does a loop have? Is it 0 or 1? So it's one of these things that is a little hard to tell, but
You just say 1. Don't you have to say the bases are non-empty or something like that?
the thing is, remember that
Yeah.
every matroid has to have some bases,
Yeah.
at least one.
So it has to have 1.
Now, the loop is a matroid of rank 0,
Yeah,
but it does have a basis, which is the empty set.
sure.
The empty set spans everything. So there's one basis. It's one of these technicalities.
Yeah.
But that's how it is. And so that means that the number of bases of a matroid is equal to that big thing, but you plug in A equals 1, B equals 1, the top polynomial of f of c equals 1, and f of loop. F of coloop is 1, and f of loop is 1. So you just get the top polynomial evaluated at 1, 1. Couldn't be easier than that. So if you have the top polynomial, you just plug in 1 for both values, and you get the number of bases. Okay. So that's my first example. This exact same analysis works for independent sets. Number of independent sets of M. So again, the independent sets of a matroid, you can split them into two groups: the ones that don't contain E and the ones that contain E. The ones that don't contain E are the independent sets of the deletion, and the ones that contain E are the independent sets of the contraction with E appended to them. For this, you have to remind yourself of look up the definition of the deletion and contraction and make sure that that's true. But there's just nothing to say here once you check the definitions. 2, again, is easy. And so, again, we have a Todd-Grothendieck invariant where, again, A is equal to 1 and B is equal to 1 because there's no coefficients here. And so all we have to do now is find how many independent sets does a coloop have?
2.
Well, 2. The empty set is independent and the coloop is independent. And how many independent sets does the loop have?
1.
Well, here the empty set is independent, but the loop is dependent because it's a loop. It has rank 0. So a loop has one independent subset, and therefore the number of independent sets of the matroid is just the top polynomial at 2, 1. Okay? Again, it couldn't be much easier than this. So if you have the top polynomial, and immediately you have the same number of independent sets. Okay, next one. spanning sets. Now,
You mean the sets that contain a basis?
so spanning sets are the sets that contain a basis. So the closure of them should be the whole matroid. Okay? The students in Colombia have thought about this more than students in San Francisco have, because one of the questions in their exam was about spanning sets, and something you might want to think about. One thing that I asked them to prove is that the number of spanning sets of the matroid is equal to the number of independent sets of the dual matroid. It's a nice exercise, which students in Colombia did and students in San Francisco should do. And so I could just say, spanning sets satisfy the same recursion, and I could ask you to fill in the details, and you'll see that it's true. Let's actually go ahead and prove this in a different way, using this. The spanning sets of the matroid are the independent sets of the dual matroid. Right? Now, independent sets satisfy deletion contraction. So this is the same as deleting and contracting for E not a loop or a coloop in the dual matroid. Okay? But now you can remind yourselves that deleting an element in the dual is the same thing as contracting it in the original matroid. So this is the same thing as the independent sets of the dual of the contraction. And these are the independent sets of the dual of the deletion. Okay. And now I have the independent sets of a dual matroid are the spanning sets of the matroid. Okay. And if E is not a loop or a coloop in the dual, that means that E is not a coloop or a loop in the matroid, which is kind of everything works out nicely, and by duality, you have the same thing, the same recurrence. The second one also checks out, and so again, you can just apply the result that we have. A is equal to 1, B is equal to 1. How many spanning sets does a coloop have? I'll ask you to do this in two ways. So first of all, directly, if you have a coloop, what do you need to span it?
Its own span. Or what do you need to span
The
it?
coloop, you need the coloop to span the coloop. The empty set does not span the coloop. So this is 1. But another way that you could do this is to say, well, this is the independent sets of the dual matroid. The dual matroid is the loop. The independent sets of the loop is one of them. Spanning sets of the loop. Well, now it's a loop. It has rank 0. And so the loop spans the loop, but also the empty set spans the loop. So this is 2. Or you could say the spanning sets of the loop are the independent sets of the coloop by duality, and you get 2. Either way. The point is that this allows you to plug in to this machinery and say that the spanning sets are counted by the Tutte polynomial at 1, 2.
So does that kind of relationship work? If you wanted to know something of the dual, can you, in general, just flip the...
It's kind of interesting, right? I mean, duality behaves amazingly nicely in this argument.
Yeah.
And it's something you should think about. We'll get to that. Yeah, actually, I'll even write that out. Note that the Tutte polynomial and duality seem to interact very nicely. And the question is, how nicely? We'll see. We'll see that it's very nicely. So, I mean, I can tell you how nicely it is. If you want the Tutte polynomial of the dual, what is the simplest possible thing you could hope for?
T sub m of y comma x.
The duality just flips x and y. And it's true. So it's kind of the dream situation. It behaves as nicely as you could possibly hope for. And we'll see. We'll prove this. Okay. And that explains why, by going from independence sets to spanning sets, all you have to do is flip the 2 and the 1.
Same thing here too, right?
And for bases, well, the bases of the matroid are basically, the number of bases of the matroid equals the number of bases of the dual matroid. And that's anticipated by the fact that if you flip the 2 once, nothing happens. Okay, nice. Next example is an even easier example. What is the easiest possible invariant you can think of for a matroid? The easiest number you could associate to a matroid.
The size of the ground set or the rank of the thing? Or?
So the rank is pretty easy.
Yeah.
The number of elements is even easier.
Yeah.
Because we define a matroid to be a set and something.
Right.
So the size of the set is the easiest thing possible. Well, that doesn't quite satisfy this, but this does. 2 to the number of elements of the matroid.
When you say number m, that's the cardinality
This is the
of E.
cardinality of E, where m is E, comma, whatever you want to define it. Bases or whatever. Size of the ground set. What does the first property say? 2 to the number of elements of the matroid equals 2 to the number in the deletion plus 2 to the number in the contraction. That's true, right?
Mm-hmm.
This is 2 to the n. This is 2 to the n minus 1. This is 2 to the n minus 1. Nothing to say. 2, well, easy.
Can we have a moment to try one of the easy ones to make sure they're really easy?
Let's try this easy one. Sounds good. So 2 to the number of elements of the matroid is equal to,
Yeah.
I said it should be f of the loop. So it should be 2 to the number of elements in a loop or in a coloop
Yeah.
times 2 to the number of elements in the deletion.
All right, that's easy.
That's pretty easy.
I'll take it.
So 2 to the n equals 2 times 2 to the n minus 1. And so what do we get? We get that, again, a is equal to 1, b is equal to 1, 2 to the number of elements in the loop is 2, 2 to the number of elements in a coloop is 2, and so 2 to the number of elements of the matroid equals the Tutte polynomial evaluated at 2, 2. And again, a matroid and its dual have the same ground set, so when you flip the 2's, you should be getting the same answer. And so if you want the number of elements of the matroid, then you just take the log of the Tutte polynomial. So again, if I just give you a Tutte polynomial, you can tell me how many elements the matroid has. Just plug in 2, 2, and take the log. Okay. What's the next easiest invariant of a matroid? Is the rank problem. And I'm going to show you that you can also read off the rank immediately from the Tutte polynomial. Rank. Now, notice that I labeled the other ones A, B, C, D, but I'm not going to label this guy E because this is not Todd-Grothendieck invariant. You can read it off from the Tutte polynomial, but not in this way. The way you do this is you say, you remind yourself of the definition of, or I guess I stated this is a theorem, right? That the Tutte polynomial was equal to this polynomial. Okay. So when I do this, I get a big mess of x's and y's, and the question is, how do I do that? How do I take that big polynomial and read off the rank? Well, here's the rank of the matroid. So let's forget about these y's for a moment. All the x's that appear are x minus 1 to the rank of m minus something. Now when A is the empty set, you get x minus 1 to the rank of m. Okay. And when A is other things, you get x minus 1 ranked to the m minus something. And so the highest degree that you have in x here is exactly the rank. So the R of m is the degree of x in the Tutte polynomial. So if I give you a Tutte polynomial, and if you need the rank, all you do is look for the largest power of x around, and that's the rank. Okay. So that's pretty amazing. I mean, all these things that we associate to the matroid are immediately read off from the Tutte polynomial. So from the Tutte polynomial, you can read off all these different things. These and more. And that's why we like the Tutte polynomial, and that's why we want to compute it. If we learn how to compute Tutte polynomials, then we can compute any of these things immediately. Okay? Now, I should also be honest and of course tell you that not everything goes in this way. And for example, I talked about number of bases, number of independent sets, number of spanning sets. But for example, I didn't put number of circuits, or number of flats. And the reason is that these are not Todd-Grothendieck invariants. Can you read off the number of circuits from Tutte polynomial? I'm not sure, actually. But definitely not in this easy way. I mean, it's not a Todd-Grothendieck invariant. Okay. So, but not everything. I'm pretty sure, actually, with my question that I just asked is just not true, and so I'm going to leave that to you as an exercise. Is to well, I'm going to give you a hint for this exercise, but find two matroids m and m prime with the same Tutte polynomial. but a different number of circuits a different number of flats to the we just write the flats as a lattice, right? So the number of elements of the lattice of flats of this guy is not the same as the number of elements of the lattice of flats of this one. Now, what's the hardest part of this question? The hardest part of this question is this one. How on earth are you going to find two matroids that have the same top polynomial, but they're different?
Yeah.
If they have the same top polynomial, that means they have the same number of elements, the same rank, the same number of bases, the same number of independent sets. So this is not easy, but it's possible. And actually, if we have time, I'll just draw these for you, and then I'll ask you to check that. I'll draw an example for you of two matroids that have the same top polynomial, even though they're different matroids. And I'm pretty sure that if you check that, we're going to see that they don't have the same number of the other things. Okay, so this says that we can compute a lot of invariants of a matroid in terms of the top polynomial. And I want to give you even more examples of this.
So did you even mention last time that there's matroids that are non-isomorphic that have the same?
I didn't mention it last time, but it is true that
Yeah.
two matroids exist that are not isomorphic but have the same top polynomial. Actually, there's another one that we should talk about before I continue, which is the characteristic polynomial. So we saw that we proved that the characteristic polynomial equals the one at the deletion minus the one at the contraction. And I asked you guys to do it as an exercise that the second property also holds for a loop or a co-loop. And so this allows us to compute also the characteristic polynomial in terms of the top polynomial. How do I do that? Well, I need A, B. Now, A and B are these coefficients, and for the first time we have a coefficient that is not 1. Now, I need A and B, and then I need the characteristic polynomial of the co-loop and the characteristic polynomial of the loop. Okay. Which is a tiny bit harder than these other things that we computed so far. But it's still pretty easy. So, characteristic polynomial of the co-loop. We saw several ways of doing this. One of them is to draw the lattice of flats. Now, the co-loop has rank 1. The empty set has rank 0, so this is the lattice of flats. Then you find the Mobius function, which is 1 here and -1 here. And that means that the characteristic polynomial is q minus 1. Okay. For the loop, this is harder, actually. So what does this lattice look like?
Just one dot.
Here, the lattice looks like this. It only has one element. What is the Mobius function of this guy?
1.
Is it 1
0.
or is it 0? So it's again one of these things where you have to make a choice and you have to make the right choice. But I mean, do you see why it's 1?
Yeah.
Do you see why it's 0?
Yeah.
I mean, there's reason for both. I mean, it's 1 because we said that at the bottom element the Mobius function should be 1. But it's 0 because we said that below every element things should add up to 0. And what is it going to be? Well, 0. That's what you need so that things work out nicely.
So it's just 0?
It's 0.
That makes sense. Yeah.
It works out if you think about it back in the colorings problem.
Yeah.
There's no way to color a loop.
Yeah, you can't color it.
Exactly. I mean, that's why I say that you need to choose this so that it's consistent with what we've done.
Right.
So, for example, if you think of a loop as a graph that has one loop, and this thing is supposed to be counting colorings, then you're supposed to color a loop, but you can't. So this should be 0.
We proved that for a loopless graph.
A loop is.
We proved it for a loopless graph.
We proved that.
Right.
Oh, you
for a graph with no loops. So we would be able to use that formula.
Right.
Okay, so then so you proved that the chromatic polynomial matches the
Well, you
characteristic polynomial for loopless graphs, and if you want that to extend to graphs with loops, then you need to make this equal to 0.
Because just any graph has a loop in it, and you can't color it, even if it has more than just that loop, right? So,
Yeah. For sure, you need a 0 for the theorem to be true that I'm going to put here, which is that. And again, it might be the case that to generalize a different theorem, you might need a different convention, but the convention we need here is this one.
The usual convention.
And it is the usual convention, yeah. What do we get? We get A is 1, so that's not there. B is -1, so we get -1 to the rank of the matroid. Then we get the Tutte polynomial of f of the coloop is q minus 1 divided by b, which is -1. So that's 1 minus q. And then we're supposed to put f of the loop here, which is 0. So this is the characteristic polynomial. Okay. Now, hopefully I convinced you guys that the computing characteristic polynomials is a useful thing. And this shows that if you have the Tutte polynomial, then you immediately have that important polynomial already.
Can I ask you a quick question?
Yep.
Oops. I think I'm missing something, but it feels like when I plug that stuff in to the big sum, I'm going to get, oh, never mind. I'm going to get exactly what I want. It's the sum part.
That's a good point. We have a big sum that defines the Tutte polynomial, and we also have a big sum that defines the characteristic polynomial with this formula. And if you plug in both things here, then you're going to get an identity, which is another way of proving this theorem and a confirmation that we really should have put a 0 here. Okay. Let's talk about applications in graphs. In graph theory. Let's say that you have a graph. Maybe I'll call it V for vertices, E for edges. And what are some of the things that you like to do for a graph? Well, one of the things that we like to do is count colorings. This is called the chromatic polynomial. Proper Q colorings of V. And of course, you guys proved that this matches that characteristic polynomial, and so therefore the formula that holds for the chromatic polynomial. And did I say this word already? Chromatic polynomial? If I haven't, this is the name that graph theorists give to this polynomial. Chromatic polynomial is the one that counts colorings of the vertices. And the chromatic polynomial is given by that exact formula, of course.
So they call it the chromatic polynomial without the extra Q power out triangle.
Right.
Okay. Then we want an R of M.
I want the rank, which for a graph, the rank is number of vertices minus number of connected components. Okay. But I'm a little bit worried. I think I want Q to the connected components. This is what you guys proved.
So that guy is a different symbol than this guy, or just
So people use the same symbol,
but that means
which is to some extent justified because it's basically the same polynomial, but it's a little bit different because there's just this extra factor of Q that it's good to keep in mind. So whenever you write these formulas, just be careful not to do them wrong, like I did even in the homework. So this follows from that. Okay, but that's not the only thing. Okay, there's another thing that people in graph theory like to count, which is trying to see how much time I have left to see if I should do the short example or the long example. Let's do the short example so we don't rush it. People like to count flows in a graph. And so what's a flow? Let's say that you have any orientation. Orient the edges in any way. In any fixed way. Okay. So maybe here's your graph. And now you're going to take each edge and orient it in some way. It doesn't matter how, but maybe let's do it from the top to the bottom. But actually, let's not do it from the top to the bottom because I don't want to mislead you into thinking that this is acyclic. You can have cycles in this orientation. Okay. So you do that in some random way. And now, what you want to do is consider flows in this graph. Okay, and so really you should think of this as a network flow. So there's maybe water flowing through, or maybe internet users or whatever it is. And in any one of these flow situations, you have this Kirchoff's law, which is a big name for just saying that at each vertex, whatever flows in has to flow out also. It's conservation of flow. So if you take any vertex, and you look at all the things that are flowing in and the things that are flowing out. So these guys are flowing in, these guys are flowing out. Then you have conservation of flow, meaning that now what you're doing is you're assigning a number to each one of these guys. So each edge has a certain flow. And you need conservation of flow, meaning that the inflow is equal to the outflow. Okay. And so the question is, can you do this? How many ways are there to do this? And so on. Putting flows on each edge so that this thing is really flowing and there's nothing getting stuck in any of the vertices. Whatever is flowing into a vertex is also flowing out. How do you address sinks? The question then is what numbers are you using? Are they numbers or what are they? Because as long as you can define addition, you can do this. And so the way that people usually do that is by considering flows mod q. Okay. So really what we want to do is assign a flow, which is a function from edges to zq that conserves the flow. So satisfying conservation of flow. It's not clear even that you should be able to do this. It's not clear whether you should be able to or not. Now,
You mean non-trivially?
non-trivially, so you can put a flow of 0 on every edge, but that's not what you want to do. So you want an interesting flow, and actually what you want is a flow that's interesting enough that no edge is wasted. So really, what we're interested in is flows that are never 0. Nowhere 0 flows on G over ZQ.
That's just the same as if it was 0, you kind of just throw out that edge or something. So
Exactly, because if you're going to put flow 0, then you might as well not have that edge. You're not flowing anything on there. Okay. And this function is called f of q. Okay. Number of nowhere 0 flows. And maybe another exercise that I'll give you is, first of all, draw this graph because I don't have it on my notes, and then put a flow on this thing to convince yourselves that it's possible. And I'll let you use whatever q you want to use. Okay.
Do you mean q to be prime or q is any number?
Q is any integer. Because all I need is my additive structure, so
Yeah.
all I care is that these guys are kind of integers mod q. Okay. Claim. Flow is generalized Tutte-Grothendieck invariant. With a minus sign on the deletion. So let me just rearrange this and write it as the flows on the graph plus the flows on the deletion equals the flows on the contraction. And again, this is for E, not a loop or a coloop. So this is what I'm going to show to you guys now. How are we going to do this? Well, let me draw the 3 graphs. G, G with E deleted, G with E contracted. Okay. So here's G, here's E, and maybe I'll put colors here to say that these guys are flowing in and then flowing out. And these guys are flowing out and then flowing in. Okay. So this is what what my directed guy looks like. Okay. And now let me draw the same graph with E deleted and with D E contracted. G deleted, E deleted, E contracted. So here I have the same picture. Except I deleted the edge. So looks like this, looks like this, looks like this. And here I contracted. So now this looks like these guys are going in and then they're going out over here. And these guys are coming out of here and coming into here. Okay. What I'm claiming is that the Q flows on this guy can be separated into flows of this guy plus flows of this guy. That's what I'm claiming, that the number of flows of this one equals the number of flows of this one plus the number of flows of this one. Okay. So maybe I'll call this inflow I1, and so I1, and O2, outflow 2, outflow 2. And then here, this will be outflow 1, inflow 2, inflow 2, outflow 1, outflow 1, inflow 2. Okay. So the only difference in these three graphs is just whatever happens at E, right? Now, what do I need to happen here for this to be a flow? I need that the I1 plus I2 equals O1 plus O2. This is what I need if this is going to be a flow. And let me rewrite this as I1 minus O1 equals I1 minus O1 plus I2 minus O2 is equal to 0. Okay. What do I need for this guy to be a flow? I need to have flow conservation here, meaning that I1 is equal to O1, and flow conservation here, meaning that I2 is equal to O2. Okay. And what do I need here? I need that I1 minus O1 plus, no. To have conservation at this vertex, I need that the flow going in is equal to the flow going out. And to have conservation at the second vertex, I need that the flow going in, I2 plus E, should be equal to the flow coming out. In other words, so here I need this, here I need this, and here I can rewrite this as I1 minus O1 is equal to E, and I2 minus O2 is equal to minus E. Okay? So now let's look at a flow here. There's two cases. These guys add up to 0. And the question is this 0 plus 0? Or is this E plus minus E where E is not 0? So this is 0 plus 0 equals 0. Or E plus minus E equals 0 for E not equal to 0. These are the two kinds of flows that you could have. If this is 0 plus 0 equals 0, then really you can think of as having already conservation of flow going this way and going this way. And so these flows that have 0 plus 0 equals 0 here are exactly the flows of this guy. Whereas if I'm in this situation, and I have that this flow is E and this flow is negative E, then I can't just separate, because I would have a flow of E in this direction and a flow of E in this direction. But I can counter that by adding this extra edge, which fixes the flow. So now it is a flow, and E is not equal to 0. So the flow that I'm putting on this guy is not 0, which is not supposed to be, because I have a nowhere 0 flow. Okay? And so these guys become these guys, and these guys become these guys. And that's the proof. That proves this. And again, the second one is the same argument but easier. And what this shows is that this is equal to minus 1 to the edges minus vertices plus connected components of the top polynomial at 0, comma 1 minus q. So if you are able to compute top polynomials, you're able to compute these guys, which are called flow polynomials. So this is another application of top polynomials to graph theory. Okay. All right.
Federico? Does this Q have, like the Q in the graph thing had to do with the number of colors we started with. Does this Q have some similar, does it have a meaning? Like which Q you?
So it's the number of flows, the number of, you're flowing over ZQ. So Q is the number of possibilities you have to put on each edge.
It's the number of choices that you're going to make for flows. I got you.
James, could you move just thank you. I do try. I put it up. It's always nice to climb the stairs with someone else.
You guys, I used to climb up to the 9th floor. I haven't done it in quite a while, but I thought some exercise for
Yeah.
You guys were sitting at the other end of the room.
It's amusing my students.